Welcome back, everyone. We're here for part 4 of the 1.3 notes. So we are on the third page now, and we're looking at a graphical example before we get to some basic techniques. So if I look at my graph here, I've labeled the x and y axis, so the original picture didn't have it labeled. I would definitely always label your axis if you can. So we've got all these graphs here. We've got F and G. So G is in blue, F is in a sort of a pink magenta sort of color. We need to evaluate these limits. We definitely have some discontinuities. So we'll note there's going to be an issue for F at -2 and an issue for G at 1. So we need to be careful of those when we combine these functions. So let's go ahead and take a look. So the limit as x approaches 3 of 2f of x plus g of x. All right, so let's look over at 3. So we've got our two graphs there, and we have a bit of a problem. All right, so if we look at f, all right, what is the limit of f at 3? Well, from the left, I can see it's approaching 0. What about from the right? Well, there's no graph, right? Our domain ends. So if our domain ends, then the limit as x approaches 3 from the left of f of x is 0. But the limit from the right doesn't exist. So we can only define this limit then if we're approaching from the left-hand side. So, back a moment here, let's erase that. So, going back to our limit here, this limit does not exist, right? But it would if we took the limit as x approaches 3 from the left of 2f plus g. So if we did take 2f plus g, then we would have, 2 times 0 plus g is approaching 1. So it would equal 1 if we were taking it from the left. But as it is, it does not exist because we are unable to check the right-hand side. So note our answer would be does not exist. Okay, so then what about B? The limit as x approaches 1. Again, we're going to have an issue with g of x at 1. That limit does not exist. So it's not even that it's 0, which we would also have to worry about for our limit, but this one is also not going to exist because the limit as x approaches 1 of g of x does not exist. So what I'm trying to point out here with these examples is not the easy cases, right? Graphical examples are actually pretty easy with limits. We'll look at some trickier ones as well, but I want to point out kind of those specific distinctions or specific cases where our limits existing are going to be tricky. Put a little line between these. Okay, and then we'll look at -2. So at -2, we want to know what f times g is. So let's look. So g is approaching -1, and f is, well, it has a hole there. Do we have to worry about a hole for the limit? No. Because from the left and the right, we're approaching the same value, which in this case is 1. So remember, for that limit, we do not care about the actual function value. We only care about what we're approaching. All right, so let's go back. And we'll zoom in a bit. And we'll evaluate this. So we're going to have 1 times -1, which equals -1. Now, the other example we're going to look at that's a little bit trickier is compositions, especially when compositions are not continuous. But that'll be for another day. Okay, so we'll go down now to kind of the basic technique problems. So we'll start with factoring. Of course, this is going to be the easiest one to identify. So when we're factoring, we could be factoring a quadratic, we could be factoring a difference of cubes, which we can see here there's going to be a difference of cubes, or we could be factoring by grouping, right? So factoring by grouping, or if factoring by grouping doesn't work, synthetic division, which hopefully you don't have to use because synthetic division is a little bit painful, but usually the denominator will kind of indicate whether you're going to be using that. So again, quadratic, difference, sum of cubes, grouping, and synthetic division. Or long division, if you want to call it that. So those 4 techniques are going to show up, and you're going to see those. So if any of these you feel a little rusty on, I would definitely review some quadratic factoring, difference, sum of cubes factoring, grouping, and synthetic division. So for our first limit, we can see that we've got a difference of cubes here. So this is x cubed minus 3 cubed, which is nice because we want to get rid of that denominator. So what we'll notice first is if I did direct substitution, I'm going to get 0 divided by 0 because I have 27 minus 27 in the numerator, 3 minus 3 in the denominator. So again, 0 divided by 0 means more work is needed. Always, 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 always is going to mean that there's more work needed because we don't know what 0 divided by 0 means. It's undefined. So it could exist. It could not exist. We have to figure out some other method to figure out what it's going to look like. So this one's pretty obvious. We're going to have to factor. So let's go ahead and start. So I'm also going to add in one detail. Until we reach the direct substitution step, when we've simplified all of our work, that's when your limit notation goes away. So every step in your work should have a limit expression until you can apply the direct substitution step. So that means that your work's going to have to be a little bit more formal as we work through these limits. So let's factor our difference of cubes here. So again, for difference of cubes, we're going to be using SOAP. So it's the same. So we'll have x minus 3. So again, so whatever the sign is of our original expression, difference or sum, that's going to be the same for our first binomial. And then opposite is going to be plus, right? So the opposite of subtraction is addition, and then the last term will always be positive. So for the first binomial, it's just going to be the uncubed terms there, so x and 3. And then it's going to be the squares on the outside, so x squared and 3 squared, which is 9. And then in the middle is the product of the two numbers, x and 3. So we're going to get 3x. Okay, and so that will always be how it factors. Again, I would review this and do a couple of examples to familiarize yourself with it if it's been a while. But obviously, a lot of these examples, there's going to be a giveaway on what part of the expression looks like. So we're going to get cancellation here, which is wonderful. And we're going to end up with the limit as x approaches 3 of that trinomial term, since our binomials cancel. So this graph has a hole in it. But we don't need to reference the graph. Okay. So then now if I look at this, I have no more simplification to do. Now I'm going to use direct substitution, and I can drop that limit notation. So I'm going to plug in the 3. So we'll have 3 squared plus 3 times 3 plus 9, which is 9 plus 9 plus 9. And it is 27. Okay, and you can graph this to verify. So, very common technique. And 2 and 3 there are going to be similar examples. So for number 2, it looks like grouping. So if I had to guess, I would try grouping. If not, then synthetic division, because you have 4 terms. So there's no factoring method besides grouping for those. And then for 3, just a quick note, this delta x, this is a very traditional variable to use. Delta x is just like any other variable, right? Any other letter that you would use. But it's typically, you'll see it in physics as, some minuscule change between 2 x values, something like that. But it is a variable quantity because we're letting delta x approach 0, which means we're letting delta x change. So for these examples, if you don't like the delta x, just call it something else. Typically h or y would be my recommendation. So make this x plus h and h, or x plus y and y. Again, variables can be changed as long as you remain consistent in your work. And for those 2 examples, I'm going to let you do them on your own. We'll probably have discussed them in class, but you can also check the notes online. Okay, so then the second common technique is going to be rationalizing. And, rationalizing, when you learned it in middle school, it was more in the denominator. So you would rationalize the denominator so that your numbers look nicer, essentially, is kind of why that technique became popularized. There's no reason to rationalize a number. And the reason why we are going to rationalize, however, is because it's going to help us solve. So the whole point of rationalizing for us is to help us solve. So these 2 examples I have, we're actually going to rationalize the numerator, because our numerator has the radical term, but we will also need to rationalize the denominator. So it's not necessarily one spot or the other. It's just wherever the square root is, right? So if you have a square root and some other stuff on the bottom, or if you have some stuff on top and the square root on the bottom, the root portion is where you're going to rationalize, wherever it's located. And the way that you're typically going to know that you rationalize is by first doing what we always do with a limit, direct substitution. So plug in 16 for x, we'll get 4 minus 4 on the top, because the square root of 16 is 4, and then 16 minus 16 is 0. So again, indeterminate form means more work. So let's go ahead and do the first example here. So we've got the limit as x approaches 16 of, let's go back. We don't need to rewrite that expression. We need to alter the expression. So we're going to multiply and divide by the conjugate. So the conjugate is completed by creating a difference of squares if you have a binomial set of terms. You can also have 3 terms, and so if you have 3 terms, you might have to think a little bit about how the conjugate would look like. But the sign between the radical expression and the non-radical expression is going to change. So we'll have 4 plus rad x over 4 plus rad x. So we're really just multiplying this by 1. So again, that common technique of conveniently multiplying. I'm going to change colors here for a second. Okay, so we'll have the limit as x approaches 16. So now the benefit of rationalizing is that our numerator is just a difference of squares. So it's going to be 16 minus x in the numerator over, I still have x minus 16, and then that's going to be times our conjugate, 4 plus rad x. And here's where we can see why this method matters. Now we're going to be able to get cancellation. However, our expression is not quite equivalent, right? X minus 16 and 16 minus x are not the same. So the typical way that if you don't obviously see what this is going to become would be to factor out a negative. Looks like from the numerator is going to be the easiest. So we're going to get the limit as x approaches 16. Negative 1 times x minus 16 over x minus 16 times 4 plus rad x. Again, you don't have to show this step. You can just cancel at that previous step, but I'll be a little bit more formal here for our notes. So those are going to cancel. So we're going to be left with the limit as x approaches 16 of negative 1 over 4 plus rad x. So note, still have that limit notation. Haven't dropped that limit notation at all. But now we can, because our direct substitution is just going to work. So we've got negative 1 over 4 plus the square root of 16, which is 8. So the answer is negative 1/8. So again, that second example is going to be for you to do on your own. You can check the notes online, and we'll probably have discussed these in class. But the key idea here is that rationalizing and keeping that limit notation in your work until you're ready to directly substitute. Make sure to show me that in your work. Okay. And then last technique is going to be simplifying complex fractions. So if we look at that, whoops. Number 2 is actually already simplified. Number 1 isn't quite. So number 1, it's probably going to be a better idea to rewrite the expression. But note, exponents and the way you write exponents is going to be written in many different ways. So be ready for that. So note 3 plus h to the negative 1 power is the same as 1 over 3 plus h minus 3 to the negative 1, which is just 1/3. So I would rewrite that first. And then you can plug in h equals 0 in your direct substitution, and you'll get 0 divided by 0. But I will skip that step here so we can just finish this example. So the question is, well, what am I going to do with this complex fraction? So I've got a fraction within a fraction itself, right? The whole thing. So we're going to do what we always do with fractions. If we want to combine them, you need a common denominator. So I'm going to multiply by 3 over 3 and multiply by 3 plus h over 3 plus h, right? Same thing that we do typically with any fractions that we want to combine through addition or subtraction. And let me zoom out a little bit so we can still see it. So we're going to end up with 3 minus quantity 3 plus h in that top numerator, all over our common denominator then is 3 times quantity 3 plus h all over h. But that all over h part we can again get rid of if we multiplied by 1 over h times 1 over h. Right, so those are going to cancel, and really the h is just going to enter our new denominator here. And this will always be true, so you don't necessarily have to show this step. Okay, so let's zoom in a little bit. And be careful. Keep parentheses with binomial quantities, because this negative 1 is going to have to distribute. So just be very careful with your work on some of these. It gets messy and it's easy to make small mistakes. Okay, so this is really going to be 3 minus h. So 3's are going to cancel. So what we're really going to end up with is negative h over h times 3 plus h. And our h's are going to cancel as well. So you saw this in your summer assignment and in the practice chapter P, where we did the difference quotient and we had to cancel out that h term. Same idea here. We're really just computing derivatives and not realizing it. But you don't need to know that yet. So we'll simplify to negative 1 over 3 times 3 plus h, and then direct substitution. We'll get negative 1 over 3 times 3, which is 9. So negative 1/9 will be our answer. So those are the 3 most common techniques besides direct substitution. So complex fractions, rationalizing, factoring, and expanding. I would, when you're doing the homework, kind of think about how you're identifying those things. And then again, the second example will be for you to do on your own and check the notes for. So the squeeze theorem we discussed in the second part. There are some special trig limits down here. So these special trig limits are limits that you need to know. And I'll probably provide a separate video with proof of at least the first one. You can prove all three of these. But we'll probably do a proof of the first one that you'll be able to see. And I just want to note that the reciprocal is also true for that first limit. It's not true for the other ones, right? 0 over 1 and 1 over 0 are not equivalent. But 1 over 1 is equivalent to 1 over 1. So it can be written both ways. It's interchangeable. So the sign doesn't matter where it is. And the key for this, and you'll see this with the proof as well, is that what matters is those two things are matching. So you're going to get something like sine 5x over 5x as x goes to 0, right? So if you have a limit of that, that's also 1, right? So as long as the angular argument matches the variable quantity here, it will always equal 1. All right, so we're going to zoom out here. So after that, we've got some trig limits to look at and then some additional exercises. So we'll finish with the trig limits. So we're going to be using this first one directly here. We can see we've got sine of 9x over x, but it's not quite what we want, right? What I would want this to be is sine of 9x over 9x. If that were true, that would equal 1. However, that 9 is not there. So is there a way we can artificially bring in the 9 without violating the expression? Yes. Just multiply by 9 over 9. So we'll get the limit as x goes to 0 of, 9 sine 9x all over 9x. Okay, so then with that, we can simply factor out the 9 here, right? Just factor it out. That's one of our properties of limits. And then we're left with the limit as x goes to 0, sine 9x over 9x, which equals 9. And we're done. So again, keep that limit notation in, though, until you're applying that specific special trig limit. Okay. So let's take a look at number 2. So we got cosine theta tan theta over theta. So if we plug in 0, we're going to get 0 over 0. So now we're probably going to want to play around with this a little bit and see what we get. So let's go ahead and think back to simplifying trig expressions, or proving trig identities even. A lot of the things that you'll see will be from that. So tangent is the same as sine over cosine, which gives us some convenient cancellation, since this is cosine over 1. So then we're left with the limit as x goes to 0, sine theta divided by theta, which is, of course, equal to 1 by our box above. Now note, we still get 0 divided by 0, though, with our direct substitution. So direct substitution doesn't yield our answer. We have to do a bit of simplifying. For number 3, we've got secant. So let's see. So if we do direct substitution, we'll have pi times secant of, pi. Okay, so what is secant of pi? Let's think about that. So our secant graph, again, is the reciprocal of the cosine graph. Let's draw a little cosine graph here. So 0 to 2 pi. It's pi. So again, we're between 1 and negative 1. So if I think of my secant graph, the reciprocal is going to be undefined when we divide by 0. So our secant graph is going to look like this. But at pi, I can see it's the same as cosine of pi, which is just -1. So knowing the graphs is going to be really useful as well for trig functions, because we don't have an analytical method for secant, right? There's no factoring rule, there's no rationalizing rule necessarily, so referring to graphs can be very useful. So we're going to end up with pi times -1, which is just -pi. Okay, and our last one, let's see. This one looks complicated. Oh. And no, for number 3, I just did direct substitution, right? No method needed. So don't assume that you have to use some special trig limit until you get that 0 divided by 0. So we'll do the same thing here. So let's see. So at 0, tangent is 0, sine is 0, cosine is 1. So this looks like it's going to work out too. So 1 minus 0 over 0 minus 1, which is -1. So again, don't assume that you need to do a special trig limit just because you see trig expressions. All right, so the additional exercises are for you all to do on your own. So I'll leave you to do that, and you can check the notes online for completed answers. Be sure to email me or come by the office hours if you have questions. So till next time.